Okay, this thing is quite simple. You see, when I have this setup here, this is a 1.5 volts battery, and this bulb operates on 1.5 volts, for example. So what happens when I set this up? At steady state, this is an open circuit. So the potential along here, let's say I take this to be 0 volts. Potential along here will propagate 1.5, 1.5, 1.5. Even after the light bulb is still 1.5. Why? Because there's no current flowing. So V equals Ri. I is 0, Ri is 0, V voltage drop is 0. So it's still 1.5 all the way to here. So this is 1.5. Okay, just check that it's correct. And at this point, let's say I close the circuit, alright? So I close the circuit. When I close the circuit, what happens? This 1.5 volts, this is 0 volts, right? So immediately, there will be a rush of current this way, right? Conventional current, right? Plus to minus. It will flow this way, this way. So let's say, for example, we take dotted line and close. We take this segment of the wire, okay? This segment of the wire, say that due to the completed circuit, there's a sudden rush towards the left here. So what will happen? Right? Say, let's not talk about the entire circuit, just this part. If let's say all the charges here in this segment of the wire move slightly to the left, what will happen? Immediately there will be a surplus of positive charges here, and there will be a deficit of positive charges, so negative charge. So these two small, infinitesimally small elements of the wire will have a little bit of positive charge, a little bit of negative charge. Okay, so when this happens, right, this is enough to generate a magnetic field, right? And this magnetic field will propagate at the speed of light to the other end. So the current will be generated so as to oppose the current here. So if the current is going this way, there will be a tiny current generated here, this way. Same thing, you take a small segment of the wire, what happens here? If the current flows this way, there will be a net positive, right? A net positive at this part here, and net negative will develop here. Just these two infinitesimally small accumulation of positive and negative charges. So does it take a lot of energy to move this little bit of charges? Not very much. Okay, not very much. And can it happen? Yes, it can happen. Just imagine that as this happens, what if more and more of the wire gets infected by this current? Right? What does it take? It's very simple. Okay, this net positive accumulation of charges, this net accumulation would move a little bit more to the left, and this net negative will move a little bit more to the right. So this shifts to the right, and as this shifts, right, the net positive and net negative shifts. As it continues to shift, it is enough for the current to continue flowing. It's enough. It doesn't take too much movement of, it doesn't take too much macroscopic movement of charges, just a little bit. Just these accumulation centers shift a little bit, then the entire segment of wire will continue to have current. And same for, it is the same for this part of the wire. So this is the counterintuitive part, because a lot of people think that, wow, you need to move a lot of charges, right? Charges cannot be created, cannot be destroyed. Then how come we are moving so much charges? Something is not adding up. Actually, it's not, right? Everything is adding up. You only need to move this infinitesimally, small accumulation centers apart from each other, and this one also apart from each other at the speed of light. So the magnetic field is propagating at the speed of light. The accumulation centers, the charge accumulation centers, are spreading out this way at the speed of light as well, and likewise for this at the speed of light. Okay, so, and how about energy, right? Energy will radiate this way, okay, this way, and as well as this way, and then this way, and then this way, and then this way, and then this way. So energy radiates out this way. So this is proven, right? Nothing to dispute about. Very counterintuitive, but proven. Okay, thank you.